called Small Satellites for Secondary Students, or S4 for short. And basically what this was a program to teach secondary students hardware implementation in science. So to bridge the gap in STEM education, because a lot of high school students would do something like TARC or something on the small scale, and then they would not have any science like this that they could do until they got to a graduate level or university level. So I was in charge of building and designing the flight hardware as well as the code that went into this. This was a board that was the final design. It had an Arduino microcontroller, and so this is where the brains of everything was, where the code ran. The base hardware also had a GPS to give location and time stamping of the data. We had real-time Wi-Fi, so we had real-time telemetry, so as the rockets or tethered balloons went up, the students could actually get their data and watch it on the screen. And so as the rocket went up, it was really neat seeing the points go. Also on there was an SD card to store the data as a secondary backup in case we lost the Wi-Fi connectivity, and a myriad of sensors of humidity, accelerometer, pressure, temperature, and magnetometer. And the board was also designed to expand to other sensors. But what this really did was in the just last year, a man named Professor Bob Twiggs came to visit us from Morehead State University. He is one of the inventors of something called a Cubesat. And a Cubesat is a 10 by 10 by 10 little centimeter satellite that gets launched off as a secondary payload off of some primary mission that goes into space. And this was really designed for graduate students at the beginning, but then now undergrads are doing it, and even high school students are building these things. And so when he saw the work we were doing here, he said, I have a launch opportunity that's coming up, and I have a spot, and if you can build a satellite in the next 3 months and deliver it to us, you can do it. And so all of our technology was fairly large traces, about 50 mils, and dip-mounted parts. Well, very quickly we learned that we had to do something different. But out of that was born T-Logo Cube. T-Logo Cube is slightly smaller than a CubeSat. It's 5 by 5 by 15 centimeters. This is a scale model of it, a model, so you can see how small this is. So the technology that we had to shrink in here was quite impressive. We were launched on November 21st in 2013 into a polar sun synchronous orbit, and we had operations for 8 weeks before radiation got a hold of us. The unique thing about the satellite is the language that we use. It's MicroLogo. It's developed by a man named Brian Silverman. And what's unique about this is, unlike C, which many of you might know, it's compiled language, and I view it as like a ball. And if you need to change it, you have to undo everything and then recompile it. Well, MicroLogo is like a book. And so if you wanted to add a functionality to it, you just write it at the end of the book. If you want to completely change the entire purpose of the satellite to turn into a repeater, you just completely change the page and rewrite the code. And so when we want to talk to it, we actually write one line in MicroLogo programs, send it up, it executes this and gives us back the answer. And I'll show you a little bit about that later. Our primary goals were to have MicroLogo work on orbit, which it did, to have the downlink telemetry, which is basically beacon packets every 20 seconds. The satellite just kind of sent out packets blindly. And then also for us to command and respond. And then we also had a magnetometer on board, just one of our instrumentations, and we did a Fourier transform in orbit. That was from Sean McNeil at Morehead State University, our partner school on this, to do a Fourier transform to get its own spin rate and precession rate. So it can actually tell us how fast it's spinning. So I'd like to quickly just kind of show the physics team of the SSU, point out Dr. Garrett Jernigan on the left, and then Hunter Mills and Ben Cunningham all the way to the left. I have to really thank for their all of their work that we put together. We worked in a really small lab in Darwin 305 together for many, many, many hours, and without their help, this project wouldn't have actually been able to get completed in the time frame. And so I'd really like to thank them, and then our advisor, Steve Anderson, who's kind of the catch-all guy that does everything. He's even over there doing cameras right now, so he does everything. So if it wasn't for this team, it wouldn't have actually happened. The one piece that I'm going to kind of express about this satellite is the radio. This radio is $11, so not $1 million missions of NASA. This is an $11 radio operating in 70 centimeter ham band at 437.465. So if you're a ham operator, you could listen to our satellite. We had 100 milliwatts transmission power. To put that in perspective, that's 4 times less power than your cell phone. And with that, we were able to get a 1 degree pass on the horizon, at 2,700 kilometers. To put that in perspective, if we have a station here, which we do, and we had one in Washington, D.C., we could relay a signal off of our satellite and talk to Washington, D.C. So that is just the distances that we're talking about. We're able to do with a little 100 milliwatt radio, which is really impressive. This is all open hardware stuff. And then to transmit to it, we just use a little amplifier at 50 watts, and we talk to about 1,500 kilometers. So when it was around 10, 15 degrees on the horizon, we could command it to do something. So like I said, we had 3 months to really develop it. This is the final version of the inside of this thing. You can see the main flight board. We use NiCod batteries because they're really nice and stable and you can really abuse them. And then the internal here, you can see the green is the magnetometer, various temperature sensors, and some of the traces that we had here. We got traces widths down to 5 mils, so an order of magnitude that we can do from when we first started this to what we can do now. So our traces are really small. We have really compact electronics. Basically in a 1/2 inch by 1/2 inch square, we can have 64 pins that we connect all surface mount. We can do this pretty much consistently every time. The unique thing I love about the satellite, and I didn't tell Garrett about it until after I did it, was I put all the names on the torque coil over here on the right of everybody from SSU that worked on this. So this satellite is going to be in orbit for the next 19 or so years. So our names are in space, which is pretty cool, I have to say. And so on the time frame, so we were launched in 700 kilometers, and you have to deorbit within 25 years per national law. And so on here, which I didn't show on the prior slide, is that there's these little solar cells that we developed that increases our drag coefficient to be able to deorbit us within the accepted parameters of roughly 19 years, depending on how our sun works. And so on November 21st, this is a video from Yasny, Russia. We were launched off a Datner rocket. It's going to go. There it is. So we're launched, it was noon their time. So we launched out of a satellite called Unisat 5, which had a bunch of other Cubesats and a few other pocket cubes, a satellite about this big. And once we got launched out, thrown out, or Unisat 5 got launched out, then we were deployed out of them. And so I don't know what the primary mission was, but they needed some kind of sun-synchronous orbit, that's why we had it. So 2 days later, we were able to hear our satellite, which is unique because most people have to wait weeks for the NORAD to tell them where their satellite is. Well, we just knew that it was going to be coming over noon and midnight every day, so we kind of scanned the skies and looked for it, and we found it through a lot of the math of Brian's brother, Barry. We kind of figured out how to track this thing. So, I don't know if I have the laser pointer. These little dots right here, this is the radio. So this is frequency space and this is time space. And so about every 20 seconds we got a packet coming in. You can notice the slant right here. That is the Doppler shift of the satellite. So just like a siren coming towards you, it has a high pitch and drops down to a low pitch. Our satellite does that. And what's kind of cool over here, we didn't know it at the time, but this is our sister satellite, Eagle 2, that launched, and you can see their packets as well, which is kind of cool. The next day, because we were excited about it, we sent our first command. This is this bright thing right here, and immediately our satellite started giving us data. So this is the data dump you can see. What I think is really neat about this is it confirmed our magnetometer is working correctly on orbit, because satellite told us it was rotating once every roughly 22 seconds. And so the antenna is coming in out of phase, the power drops, and we were able to see that it actually was rotating roughly every 22 seconds. This is a ground station right here that we use to communicate with it. It's at Lynn Garrett's house. Right now, we have a grant that we won, the Society of Physics students, to build one of these on Earth of Darwin, so we'll be able to communicate with our future satellites as well as other university satellites. And this is just kind of an example of what the data looks like. And this has all of our solar panel and all of our science data and everything in it. And we had 4 different types of packets. So moving on to the next thing, we're kind of calling it TRL6. It's kind of a split between, again, going back into the classroom, teaching micro-logo to high school students, which is what this dev board is designed to do. The high school students won't realize it, but they're actually using technology that's in space. This is the radio that's in space and the processor, and it's designed to plug into a protoboard, and so they can then add their own sensors to do whatever kind of expansion that they want to do, science, and gather and basically operate just like the way our satellite did, but on terrestrial base. But we'll be expanding this out into something that's flight-like, like this magnetometer right here. It's a 4 by 4 centimeter frame there. And we're able to connect everything over something called a one-wire network, which is a unique property of being able to use micro-logo. So we have just everything is bus, and we don't have to worry about communication cables that break and fail. And then the key science we're doing is CZT, which is cadmium zinc telluride array. It detects hard X-rays, which X-rays can only be detected from space because our atmosphere absorbs it. So if we want to look at any X-ray sources, we have to be above our atmosphere. And this was developed by Garrett Jernigan, our mentor. He's luckily enough able to provide it to us. And so this whole satellite is going to be packaged over the next year or so, and we have a launch next spring off the International Space Station. We're going to be in a 1x1 or 10x10x10 little Cubesat form factor, which is kind of exciting that we're passing this project off to the next group of students. So look forward to their talk next year probably for this. So thank you, and if there's any questions.
A few minutes for questions.
You said that it's coming off the International Space Station, so it just opens up an airlock and toss it out?
They actually use the Japanese arm, and then goes out of one of the Canadian arm is the Japanese. And there's pictures, if you look, it's kind of neat. You have these little Cubesats that are going by the solar panels. Because one of the cool things about launching off the ISS is the astronauts take pictures for you, so you actually see your satellite launch. Where we've never saw our satellite in space. Next year we'll be able to see it. Any other questions?
What do you estimate for the lifetime of the satellite?
Which one? The T-Logo Cube or the future one?
Well, they both have batteries, or one does.
Right, they both will have NICADs. The orbital lifetime of T-Logo Cube is about 19 years, and that's just related with the drag coefficients coming down. The battery lifetime, one of the surprising things about T-Logo Cube is we actually disconnected the batteries, went outside, and it just started working. And so we could technically, because of the efficiencies of our solar panels, run with no batteries. And if we were in daytime, it would work. We're kind of exploring some of the technology for the next one using supercaps, so that if batteries start to die, we can take them out of the system, and our satellite can keep on functioning when it's in sunlight. But when you go off the ISS, it's at a much lower orbit, so it's about a year or so before it decays and burns up the atmosphere.
So when you're sending commands, is there any sort of encryption protocol or anything that's there, or could anyone actually track your satellite and send?
If they had our software to be able to send it, we have checksums on every packet. So if the satellite gets some packet and it doesn't recognize it, it rejects it. So you have to have our ground-based software to actually send it up. So yeah, if that got leaked, then people could probably do that. But
Sort of a secret code.
secret code. It's safe by ignorance.
Okay.
And if I could chime in, this is a unique feature of this CubeSat. Reprogramming satellites in space is usually not allowed.
In fact, there have been hundreds of CubeSats that have been launched by various groups, and only maybe 10 have even sent beacon packets, and probably less than a handful have ever responded to commands or done anything sophisticated like, well, actually none of them have ever done anything as sophisticated as a fast Fourier transform in orbit of based on their data. That is just a whole nother level. That's the kind of thing that billion-dollar satellites usually do. And this thing, you know, basically the parts cost, what, $500?
Yeah, the flight board is about 120 and the Dodover is like 50, so
yeah.
Altogether.
We had to build it over again. Of course, we spent more money than that developing it, but.
Yeah, there's about 10 revisions of the board, but we were able to go from schematic change to a flight board with Hunter and Ben, and we could do that in 4 hours. So we could actually change something that we didn't like and have it working and testing on the ground in 4 hours.
And you made what, 10
revisions. So.
10 boards before they finally got one they liked.
Any other questions?
More questions? Okay, well, let's just thank Kevin again.